are going to start off by looking at section 7.3. So this is going to rely a little bit on what we did with 7.2, which is why I tried to go over some of that before we started. But I'll remind you again of the ASTC chart if you need it, and we'll go from there. So today we're going to look at 7.3. Tomorrow will be 7.4, and then Wednesday and Thursday will both be 7.5. So we're going to split 7.5 into 2 days. So the plan for this week is 7.3, 7.4, 7.5. All right. So remember, when you are solving a trig equation, you can have many solutions. Think of drawing like a wave and a horizontal line. Okay? They cross many times. In general, how often does an answer repeat? Every what? Every cycle, whatever a cycle is. Cycle can be different length in different graphs, but in general, it's every cycle. So what we want to do is when we're solving trig equations, we're going to find all the answers in one period first. Okay? Remember the formula that you need for the period? It's either 2 pi over b or pi over b. Okay. 2 pi over b, that's for the sine, cosine, secant, cosecant. The only ones that use the pi over b are tangent and cotangent. If you're doing it in degrees, you'd want to do a 360 over b and a 180 over b. Okay, so the first thing we have to do is we find all the answers in one cycle, okay, and we're going to do it graphically, which means we're going to find like probably an intersect. And then, to represent all solutions, we have to take into account the period of the function. So you take the solution that you found using the intersect and put plus the period times n. Where n is what does n represent? So what kind of number? It has to be an integer, yes. So what that means is you can add any multiple of the period. You can't add like a half a multiple. No, you're going to add a whole multiple of the cycle, or you can subtract a multiple of the cycle, and you'll get an answer in a later or earlier cycle. And it doesn't have to be an n. Sometimes I've seen in the book they use a k. It's the period times a variable. Generally n or k they use a lot. All right, so let's start with one that we've done before. Okay, we did this algebraically last time using the ASTC chart. All right, for today, I don't think we're going to use the ASTC chart since we're doing it graphically. We are going to use the ASTC again later in chapter 7, so that is still important. But maybe not for today. All right. First thing is, let's find the period of that. What would be the formula that I use to find the period of the trig function there? Yeah?
2 pi over b.
2 pi over b. Okay. And what is b in this case?
0.8 x.
No, b has to be a number. It has to be a number we fill in. Yep.
Just 1.
1.
Because it's nothing there.
Right, it's the coefficient of what's in front of the x. So in this case, it's a 1. So the period is 2 pi. Okay, that tells us a couple things. 1 tells you how wide of a window you need to set on the calculator. 2 tells you what to add on the end of your answer to represent all solutions. Okay? Because there's infinitely many. Okay? We're going to have a horizontal line and a wave that cross forever. So we can't write them all. So we need a way to represent them all. And that's how you do it. Okay, so let's put that in. put in sine x, put in 0.8, and I'm going to set my window to 1 cycle. There's a lot of ways to set a window that has a width of 2 pi. It's kind of like if you wanted to set a window with a width of 10 units. You could do 0 to 10. You could do 20 to 30. You could do 50 to 60, 75 to 85. There's lots of ways to get that width. What's the simplest way to get a window that's 2 pi units wide?
360 degrees.
We're going to do it in radians. So what would I want to set for my window?
2 pi.
2 pi for the...
X max.
Okay, and what about for the min?
0.
Yeah, if you do 0 to 2 pi, that will give you a window of the period. Okay, how high and low do we need to go? Well, sine only goes -1 to 1, so we'll have more than enough room with -4 to 4. That's not zoomed out too far that I won't be able to see it, but it's a lot more than I need, but that's okay. All right, and we graph it. And how many answers does it look like we get per cycle? 2. Okay, we're going to find each of them. How are we going to find them?
The intersection between the blue and the red line.
Yep, so we're going to do it as an intersect. Doesn't matter which one we do first, we just need both. So 2.21. And the other one is, let's see, 0.93. And if that's all you write, all you've done is find the answers in 1 cycle. You have not found the answers in all cycles. So what should I put on the end of each of those?
Plus 2 pi. 2 pi n.
2 pi n. So that means you can add any multiple of 2 pi to those two numbers, and you'll get another answer. Okay? You could add 2 pi. You could add 2 pi times 2, 2 pi times 10. You could add any integer multiple of 2 pi. And you could subtract it. Like if n was -1, you would minus 2 pi. That would give you an answer earlier in the cycles. Okay, so those are your 2 answers. All right, so we've done that before. But any questions on that? All right, so now we're going to take a look at what happens in a more complicated trig function. Like what if we have multiple trig functions in the problem, like sine and cosine, and we're raising them to different powers. Okay, we have to be able to get the period of that. So that's what I'm going to show you how to do. All right. Now that was equal to 0.8. We might get to some problems, and we will, where we're setting it equal to 0. Okay. So there's another one where it's equal to 0. Does anybody remember when you set something equal to 0 and solve it, what you're finding? Yeah?
X.
Well, you're finding x, but you're finding something specific. It's the roots. When you set something equal to 0, you are finding the roots, or you're finding the zeros of the trig function. Okay, so just a reminder of what that is. So if you see directions that say find the roots of the following equation, that means take the equation and set it equal to 0. All right, so how do you find the period of something that's more complicated than just a single trig function like sine? Well, First thing we have to do is find the period of each periodic term. So find the period of each periodic term. Okay, I'm going to go back to that equation that I had on the board a minute ago that was a little bit more complex, and I want to just take a look at it. How many terms are on the left-hand side of that equation? 3. What's the first term?
2 cosine.
Yep. So that's the first term. What's the second term?
Sine t.
Sine t. And the third term? 1. So the directions said find the period, not of each term, each periodic term. How many of the terms on the left side of that equation are periodic?
2.
2 of them. Periodic, for the kinds of things we're doing, means it's a trig function. 1 is not a periodic term, that's a constant term, which is plus 1. It doesn't have a cycle to it. But sine and cosine both have a cycle. So the first step is going to be find the period of this, find the period of that. One of those you should already know how to find the period of. The other one, maybe not, because it's raised to a power. Okay, but I'm going to show you how you do that. It's still going to use the same 2 formulas, pi over b and 2 pi over b. So those 2 formulas that I gave you, you can actually use them for more than I even told you you could. And I'm going to show you an example of where you can use those in other situations. Okay, so find the period of each periodic term. Then, the period of the entire problem is the least common multiple of the individual periods. It's the LCM. Okay. So like, let's say you had a term with a period of 2 pi, and you had another term with a period of 3 pi. To find the period of the whole thing, and one of them had a period of 2 pi, and another one had a period of 3 pi, start listing your multiples. Multiples of 2 pi, 2 pi, 4 pi, 6 pi, 8 pi, 9 pi, oops, sorry, 10 pi. Okay. Those are the multiples of 2 pi. Okay. Multiples of 3 pi. 3 pi, 6 pi, 9 pi, 12 pi. And the period of the whole thing is the least common multiple. So what's the smallest multiple they both have in common?
6 pi.
6 pi. So in this case, you'd be working with a period of 6 pi. Remember, the least common multiple cannot be smaller than either of the original periods. It has to be at least as big or bigger. In this case, it's bigger, 6 pi. Now, if you're thinking 12 pi, yes, 12 pi is a common multiple, but it's not the least common multiple. So we gotta use the least common multiple. All right. So now, let's go back to this one, and let's look at sine t. What's the formula we're going to use to find the period of sine t?
2 pi over 1.
2 pi over 1. It's 2 pi over b, but in this case, b is 1. That's the number in front of t. Okay, so we know the period of sine t is 2 pi. We need the period of 2 cosine squared t. Let me show you how you find that. So if you are working with anything in that situation, basically any tangent or cotangent, and a sine, cosine, secant, or cosecant to an even power, the formula you always use to find the period, if it fits one of those cases, is pi over b. Now, I put the b in absolute value because if b was negative, we wouldn't want to use the negative. The period is a measurement of how long something is, and length is always a positive number. So then, what's left? What cases haven't I put on the board?
All of those to an odd exponent.
All of them to an odd?
No, besides tan and cotangent.
Besides the tangent and cotangent. Yeah, the sine, the cosine, the secant, and the cosecant to an odd. That's where you're going to use 2 pi over b. So we've been dealing right now to the first power. So we've always been dealing with to the odd. So sine to the first power, that's why you use 2 pi over b. Cosine to the first power, that's odd. Tangent and cotangent, it doesn't matter whether it's an even or an odd. We've been using pi over b to find the formula for tangent and cotangent. And we'll continue to do that no matter what power you have. Okay, remember, b is what's in front of the x. So b is the coefficient of the argument. I can write that off to the side. Just in case you don't remember what b is. All right, so it's the same two formulas we're used to using, pi over b and 2 pi over b. We can just use them in more situations than you originally knew about. All right, so now we're going to go back to our problem and see if we can find the period of the first term, which I think was like something with cosine squared. All right, that up. Okay, we've got cosine to what kind of power?
Second.
Second, which is
Even.
even. We have cosine to an even. What does it say we should use for the formula?
Pi over b.
Pi over b. Okay, and what's b in this case?
1.
1. Okay, look at the coefficient of t. It's just a 1. So that period is just pi. So now we're getting ready to find all the solutions, but we need to set our window to 1 period. We should now know what 1 period is. What is the least common multiple between 1 pi and 2 pi?
2 pi.
Yep, 2 pi. Okay, it seems like that's going to come up a lot today. Not every problem has 2 pi, but it just seems to be a pretty popular period. Okay, any question how we know the period is 2 pi? Okay, so now that tells you two things. How to set your window and what to put on the end of your final answer once you have that later on. Okay, we are already set up to go from 0 to 2 pi. So let's type all that in. Because we are raising trig functions to powers, we got to be a little bit careful. So we want 2 cosine x squared. That is how you have to type that in on the calculator. Exactly the way I've done it, exactly the way the parentheses are. If you have the whole thing in parentheses, that would not be what we want. We don't want to square the 2 in the front. We just want to square the cosine. Okay. Now, plus sine t, that part's pretty easy. Plus 1. So we are looking for where this graph crosses the x-axis. That's what it means to equal 0. Now, if we have exactly 1 cycle, my graph should end at exactly the same height that it started at, because it's like it's wrapping around. That looks good. So that's 1 cycle of my graph. Okay, it doesn't look like a nice symmetrical wave anymore because we've complicated it. we've added another trig function to it and we squared something, so it makes it look a little more complex, which is also why we don't sketch it by hand. Yeah. Yeah, just so I know. Okay, how many times does it look like it crosses the x-axis? How many?
Once.
Once? Yeah, what we probably want to do is zoom in. I think it's pretty clear. It does not cross out here at all. It doesn't cross over here. It's just in this area. Is it once or is it twice? So what we'll do is we'll zoom in. And we're going to calculate the 0. Okay, if we calculate the 0 and it's right in the middle, then we know it only crosses once. If something crosses twice, okay, then what's going to happen is you won't get it right in the middle, you'll get it off to each side. Okay, just to kind of exaggerate it, you know, if it did something like that, that's the minimum. If the 0 is right on the minimum, then you know it only crosses or touches once. Otherwise, you get 2 answers off to the sides. Okay. All right, so let's do second calc, 0. And what I'm going to do is I'm going to do this, and then I'm going to do the minimum. And if they come out exactly the same, that proves it only crosses one time. I can also tell if it looks like it's right in the middle. I mean, it does look like it's right in the middle of it. So it's about 4.71. Now, let me calculate the minimum and just see what that comes out to. It's exactly the same. So I know it does not go any lower than 0. If it doesn't go lower than 0, then it does not cross and come back. Right? It just touches it and bounces off. All right, so that's the answer in the first cycle. How am I going to represent all solutions? Right, plus the period times n. That's all solutions. Okay. Any questions on that one? Let's try, I think I got another one of those. Let's try this one. Okay. In the last problem we did, what was it equal to? 0. So let's do this one the same way. Let's get it equal to 0. And solve it that way. Not that you can't do it this way. You could do it that way. But I'd rather do it similar to the last problem. So how would I get that equal to 0?
Subtract 10x from both sides, or subtract 3 cosine x.
Yeah, it doesn't matter. You could do it either way. You're going to get the same answers. I'll just do it the first way you said, which was to subtract cosine x from each side. Oops. Minus tangent x. Now, to find the period of that whole thing, find the period of each term. What's the formula to find the period of cosine to, what power is that to? Odd. First power, yeah. What's cosine to an odd power?
2 pi over b.
And what's b in this case?
1.
Just 1, so it's just 2 pi. What's the formula for tangent to an odd?
Pi over b.
Tangent to anything is pi over b. And what's b in that case?
1.
Yep. Remember, the b can be different in each case, because you could have a different number in front of each of those x's. We don't this time. So the period is pi over b, which is 1. And what's the LCM of 2 pi and 1 pi?
2 pi.
2 pi. Okay. So remember what that tells you. What to set your window to and what to add on the end of each answer. Okay. I am already set up for, no I'm not, I need to fix my window. Oh, it's because I zoomed in, that's why. All right, so let's set it back. Let's get rid of that. Okay, 0 to 2 pi. And now type everything in. There's no powers, so parentheses here are not anything really tricky. Just 3 cosine x. Close your argument for cosine. Minus tangent x. Close your tangent. Okay. And when we graph that, I'm going to go back, because I zoomed in, I'm going to go back to -4 to 4 on the y's. If I don't think I would have been zoomed out enough. And we know it's going to go off the screen, right? Because it has tangents. Tangent has vertical asymptotes. All I'm interested in is, can I see where it crosses the x-axis? And yeah. How many answers does it look like we get per cycle? 2. Okay, so we're going to do second calc 0. Okay, and I moved over so my cursor was on the first part, and I get 1.01. And for the second answer, I get, remember you're not doing an intersect because we put everything on one side. Okay, so you're doing a 0. You could do an intersect if you drew a horizontal line right on top of the x-axis, then you could do it that way. 2.13. And what's going to go on each of those answers?
2 pi n.
Yep, plus 2 pi n. Everybody understand why we're putting the plus 2 pi n? Okay, it's just representing this answer in the next cycle or the previous cycle. Okay, and same with this one. You got that answer down there, and you get that answer back earlier on as well. Repeats it forever. All right. Any question on that one? Okay. So no ASTC chart today because we're using the calculator. Later in chapter 7, we'll come back to that. Okay, let's try this one. What's the first thing that we want to start out by doing?
Say that again?
What's the first thing that we start out with?
Did we start out with?
Yeah.
It equals 0.
Okay, yeah, it already equals 0, so we're good. We don't have to change it around to make it equal 0. Yeah.
Find the period of each term.
Right, find the period of each term that has trigon. Sine cubed 2, this 3 does nothing. That's a vertical stretch. That doesn't affect the period. Sine cubed 2x, that all plays into the period. What's the formula for sine cubed?
2 pi over b.
Okay, so it's 2 pi
Or I guess it
over,
would be 2 pi over 2.
so this one would be 2 pi over 2. So both the cube and the 2 are affecting the period. So what's the period of sine cubed 2x?
Pi.
Pi. And again, this is just a vertical stretch. It has nothing to do with the period. Okay. How about the cosine of, well, 2 cosine x?
2 pi over
It's 2 pi over b. And what's b in this case?
1.
1. So period of the entire left-hand side is going to be
2 pi.
2 pi. Okay, so now did I zoom in? I don't think I zoomed in, so yep, I'm still good on my window. 0 to 2 pi. Now let's see if we can type all that in. This, just to make it clear what this means, sine cubed 2x, that's how you can write it on paper. It means this. It means the sine of 2x to the third power. So that's how we need to type it in. We don't want this 3. inside that bracket. We want it in front. If it was inside, then it would get cubed and it would become a 27. So this is how we do it. 3 in parentheses, sine 2x. Okay. Close your parenthesis for the argument. Close it for the trig function, and then raise it to the 3rd power. I think it looks a little clearer when I do it with brackets, but the calculator just uses parentheses. And now the second part, just make sure you get out of the exponent, minus 2 cosine x. That's how it should look when you type it in. All right, remember, we're looking for how many times it crosses the x-axis. Okay, how many times does it look like that one is crossing the x-axis?
5? Wait, 6.
I cut off the top, that doesn't matter. Yeah, it is crossing 6 times. Yep.
When you put it into the calculator, you put 3 in the front and then 3 is an exponent.
Mm-hmm.
It's supposed to be like that?
Yep, because there's a 3 in the front and a 3 as an exponent.
Oh, okay.
Just a coincidence. I mean, it could be a 4 in front and a 7 as the exponent. They don't have to be the same. But yeah, it's crossing 6 times. I already have all the intersections. I already have all the zeros, so we don't have to do each one at a time. But you'd have to find each one of them and then put plus 2 pi n. Okay, so I already have them all. So the 6 answers are 0.50, 1.25, 1.57. So those 3 in the middle are pretty close. That's the 1.25, 1.57, 1.89. Then there's a little bit of a gap and then an even bigger gap. So the next one is 2.65. And the last one skips to 4.71. And what do we need on each one of those answers?
Plus 2 pi n.
Right, I'm just not really proper notation. I'm just going to put a big plus 2 pi n on all of them. Okay, 6 would, that's a lot. Generally, you won't have that many in one question. I would say 2, 3, maybe even 4. Probably not up to 6. That's a lot. Right, but that's the cycle of what your graph looks like. That's this whole thing, and it just goes up off the screen a little. That is one cycle. So now if you wanted to see what does it look like in the next cycle, it's going to look just like that. That's the pattern that keeps repeating over and over. Okay. Any questions on that? So now let's finish up with some inequalities. It's very similar when we do inequalities to the way we do equations. When we write our answer to an inequality, it's not usually just a single number. How do we write our answer to an inequality? We write our answer as an what?
Equation.
So an equation, we write our answer as like x, and then we usually have a single number. With inequalities, though, we don't write a single number. How do we usually express our answer when you're writing an inequality?
Oh, inequalities? Isn't it like greater than equal to?
Okay, so you can write it with a greater than or equal to symbol, or what's another notation we've talked about using?
Oh, the brackets?
And when you use brackets or parentheses, you are writing and, yeah?
Period or cycle, whatever, I don't know.
Can you repeat what you just said?
I don't remember.
When you use brackets or parentheses, you're describing and what? What do the brackets and parentheses, what do you call when you write that thing down? Like when you write two parentheses with a comma between them,
Interval.
that's called a coordinate, like in geometry, but we call it something different.
Is it interval?
Yeah, it's an interval. That's why that was my hint. You're using an interval, right? So you're describing your answer as an interval. When you find an interval that works in one cycle, that interval works in every cycle. So it's exactly like an equation in that you need to put plus 2 pi n, telling me the whole interval could shift to another cycle. Not just a single answer shifting, but the whole section that works can shift. Okay, so answers are going to be intervals. Remember that if you have a vertical asymptote, that breaks your interval. You can never include a vertical asymptote in the interval. If there are vertical asymptotes in these problems, they're going to be easy to find. Okay, they're not going to be complicated. You might have an interval at like pi, or 2 pi, or 0. Okay, they're going to be easy to see. Also, remember that if you include the left edge of the window, should you include the right edge? No, because
It starts and ends.
right. This point right here is exactly the same as that point right there. It's just it's the point in the next cycle. So if you include the left edge, think of your right edge like that. Don't include it. Right? That's a full cycle, properly the way I've shown it. Okay, let's try it. Let's find where sine is less than cotangent, and they want all solutions. Okay, we could do this a couple ways. We could leave it the way it is, or we could put everything on one side and get 0 on the other. So which way do you want to do this one? Get 0 on one side, or do it the way they gave it to us? What way? This way. Okay, so then that means we're going to put sine in y1. So we're going to use sine x. We're going to put cotangent in y2. How am I going to put in cotangent?
It's like 1 divided by tangent.
1 divided by tangent. And I'm looking, if you want to think about it in terms of the colors I'm using, where the blue is under the red. Okay. Oh yeah, we should set our window to 1 cycle. What's the period of the sine function?
2 pi.
2 pi. What's the period of cotangent?
Pi.
Pi. LCM.
2 pi.
Okay. So I think I'm already set up for 2 pi. Yep, looks good. So we're looking for where the blue one is under the red one. Okay, so first of all, is the blue graph ever under the red one?
No.
Yeah, but is the blue one ever below the red one?
No.
Yeah.
I would say it is. Yeah. Like if you look at it right when it starts out, the blue one is below the red one. The red one is above. So yeah. How many sections are we going to have to describe to say where the blue is under the red? 2. You're going to have to describe this section from here to here. Call that section 1. And where else is the blue one under the red one? Or where else, let's think of it, we need to add something else to this picture. Tangent has something in it.
Vertical asymptote?
It has a vertical asymptote. Where's the left edge of my window?
Isn't it at the
it's at 0. Where's the right edge of my window?
2 pi.
2 pi. So there's a vertical asymptote somewhere, and I told you I'd make it relatively easy to see. Where does it look like the vertical asymptote is?
In the middle.
In the middle,
Yeah.
which is
Pi.
pi. So we need to put that in there. That's going to help us. So now, where is the blue under the red for the second time?
Pi to,
From here, yep,
yes, to where it meets the line.
where it meets the line. So we need to describe that section right there. Right. So we have to describe 2 separate sections. What's the symbol you always put between 2 intervals?
U.
Yep. So we need that. Now let's start with all our brackets and parentheses. Can I include the left endpoint of interval 1?
Yes.
Yes, because that's the left edge of my window, and you are always allowed to include that. Can I include the right part of interval 1?
No,
No, why not?
because that's where it intersects.
Right, that's where it intersects, and it says that it has to be under, not under or equal. Okay? So you're going to need a parenthesis on that. Okay, let's look at interval 2. Can I include the left endpoint of interval 2?
No,
No, why not?
because that is the vertical asymptote.
Right, it's on an asymptote. You can never include a point that's right on an asymptote. So no. Can I include the right endpoint of interval 2?
No.
Nope. Because I have to be under the cotangent, not equal to it. So that's how all your brackets and parentheses should look. Okay, still a little bit more we can do before we even do some more on the calculator. Where does interval 1 start?
0.
Starts at 0. Where does interval, well, we don't know. Yeah, we do know where interval 2 starts. It starts at pi. But we don't know where interval 1 stops or where interval 2 stops. That we need the calculator. So let's do second calc, intersect. So interval 1 stops at 0.90. And interval 2, second calc, intersect. Okay, interval 2 stops at 5.38. Now, what we haven't done yet is that. All we've done is find the 2 intervals in the first cycle. How often are these 2 intervals going to repeat? Every period. So we can put a plus 2 pi n on that entire interval and on that one. That means if you added 2 pi n to that and to that, you could take that whole interval, basically that section in black, and you could shift it down to right there, and you would get the next interval 1 that works. Okay. And then if you add 2 pi n to each of those numbers, you'd get the next interval 2 that works. Okay. So it's the same thing as shifting a single point, and now we're shifting a whole section by putting plus 2 pi n. I think the way the book does it is they do plus 2 pi n on every number. I just do it on the whole interval.
I have a question. After the interval, before like the or, could you add like plus 2 pi n and then the u and then the next interval, or do you just want us to like put it underneath?
No, I guess you could put it right after it.
Okay.
That'd be fine. Yeah. I guess I just want you to understand that it's outside the interval, whether you put it on the end of it or below it or next to it. Yeah. Because it's not just that number or that number, it's both numbers you'd have to shift together. All right, let's do this one, and this time I'm telling you to graph it as is. Okay, don't rearrange anything. Okay, so let's put this in. Let's do sine 2x and x squared minus 1. So I'm looking for where the trig function is equal or higher than what's on the right-hand side. What shape is the right-hand side when you graph that?
On the right-hand side?
Yeah. It's a parabola, yep. If you had said quadratic, no, that's not the shape of it. That's the kind of equation it is. It is a quadratic. It's not even an equation, it's an expression. But it is a parabola. Yeah. So it's going to have a U shape to it. And it's been shifted down 1 unit. Okay, so let's just do zoom 7. I know I'm graphing more than one cycle, but you'll see why in a second. Okay, so there's the left side. And there's the right side. And they want all solutions. Okay. Are we going to put plus the period times n on our answer? What do you think? Usually when it says all, we have to put plus period
Yes.
times n. Do you think so?
No,
No? Why not?
there's only one parabola.
There's only one parabola, right? The parabola isn't periodic. You don't get another parabola over here and then over here. You get it one time and that's it.
So because it doesn't repeat, that's
So
why we
there's
don't put it.
only-
Yeah, we're not going to put it. The parabola doesn't repeat.
So there's only two solutions, basically.
Well, there's only one
solution.
interval.
Yeah, one interval.
Yeah, where is the sine function above the parabola? That only happens between here and there. That is the only answer to this problem. That one section. It doesn't happen again anywhere else. So can we include the left endpoint?
Yes.
Yeah, because it says it can equal. And can we include the right endpoint?
Yes.
Yeah, there's no asymptotes. We're not on the edge of the window. So when we write our interval, that's what it's going to look like. Okay, we just have to find each of the numbers. So second calc intersect. So the left one is negative 0.46. And don't assume that it's symmetrical and the right one is positive 0.46. Maybe that's the case, maybe not. So let's do second calc intersect. No, it's not symmetrical. So it's 1.26. No 2 pi n, because the parabola happens once, and then it's done. All right, any question on that one? All right, so let's look at the last one. So the last one is a double inequality. That's where we're going to have 3 things. And we're going to have something kind of sandwiched between 2 things. So what we'll do is we'll graph all 3 parts. So you're going to need a y1, a y2, and a y3. And then you're going to usually look for where something is sandwiched in the middle. Okay, the first thing is I just want to look at this part in the middle. X sine x. Does anybody remember when you put something in front, what kind of transformation is that? Multiplying by a number, or multiplying in front? When you multiply by something in front, what does that do to a function?
Is it vertical or horizontal?
Vertical.
Vertical.
It's a vertical stretch. What kind of thing is that?
Letter?
It's a letter or a, no, it's not an argument. The argument is inside over here. But it's a letter, also known as a
No, not an integer.
variable.
A variable.
So what's happening in this problem is it's a variable vertical stretch, which means the bigger x gets, the bigger the vertical stretch gets. So when you get towards the origin, it's a very small vertical stretch. And then as you move away from the origin, it gets bigger. So it's going to kind of look like a wave, but it's going to grow the further away it moves from the origin. All right, so let's put in all three of these. So we've got negative x, positive x, and x sine x. Okay, so what am I looking for? I'm looking for where the wave that's going to have a variable stretch to it is going to be between the negative x line and the positive x line. The negative x line is blue, and the positive is red. So I'm looking for where this is above blue and under red. So keep that in mind. I want it to be above the blue and below the red. There's the blue. There's the red. Might have to zoom out a little bit to see it better. I'm just going to zoom out.
It looks like a W.
It does. It looks kind of like a W. When I zoom out, you're going to see more of it, so it's not going to look like a W anymore. You're going to see more of the wave.
Yeah. Oh.
So it's a variable vertical stretch. The further away you move, the bigger the stretch gets, but it always stays bounded between those two lines. Never goes outside.
Oh.
So, where are we? Let's put this over here.
Would you put in y equals?
For the y equals those three graphs. So where are we above the blue and under the red? When does that happen?
Above the blue is on the right and below the red is on the right as well.
And so that, how would you describe that in terms of like an answer? We have to describe it in terms of, think of like an interval. Yeah?
0, infinity.
Yes, from 0 to infinity. That's the answer. You will be above the blue and below the red. Now, whether I can include 0, I don't remember. It said, yeah, equal to, so that's okay. So the answer is from 0 to infinity. Okay. Any question on that one? All right, so let's try one more of those. Pretty similar, but a little different. I want to put these two graphs side by side because they're going to kind of look the same, but they're going to have different answers. Okay? And the color is really going to help you to see what's different about the graphs. Okay, so now let's do negative absolute value. So negative absolute value and positive absolute value. In the middle is the same. Okay. And this time, I think it's the same coloring that I used last time. I want to know where I am above the blue and under the red. Now, if you didn't have color, these two graphs would look identical, but they're not identical. Once it sketches it, I want you to tell me what's different. Okay, so that's the first one we did, and this is the second one. What's different?
Oh, the red and blue switch.
The what?
The red and,
No,
wait.
The red is a V.
Oh,
Yeah,
yeah.
Right.
absolutely. The
Right.
red is a V and the blue is a V as well.
Right, when we do the one on the right, the red one is the V shape, it only looks like a V shape here because we have a cross between the two lines. So black and white, these would look the same, okay? But we can see that they are not. They are different graphs. And we want to know, what did they say, above the, which one did I use for the negative? I forgot. That was
Red.
the blue. No, the blue was the negative and the red was the positive. Okay, so where am I above the blue and under the red? Okay, so look at the second one.
Negative infinity to 0 and 0 to infinity. Right?
But it can equal, they can equal each other as well, because they had the equal to's.
Yeah.
So where are we under the red and above the blue or equal?
Equal.
Yeah?
Negative infinity to infinity.
Yeah, all of the time. The question is, where are you equal or under the red and equal or above to the blue? Well, that's all of the time. You're always meeting that, no matter where you are. Okay, so that is all real numbers. And of course, because it is infinities, we never include the infinity. Now, if it didn't have the equal to, then we'd have to be a little bit more careful about describing the interval. You would have to say from negative infinity to 0 or 0 to infinity. You'd have to leave 0 out. But because of the equal to's, it actually made the answer a little bit easier. Yeah. All right. Any question on that? Okay. All right, so that's homework for tonight. Some of those are just odds. It's the 19 to 23. So actually, I could probably simplify that because it's 29, 31, 33. I could just say 29 to 37 odd. It'd be easier to write down that way. No, I forgot. It's 29 to 37 odd. So it's 5, 7, 12 to 15, that's all. 19 to 23 is odd, and 29 to 37 is odd. Okay, and if you didn't have the homework from 7.2 part 2, I will take a look at that as well tomorrow.